Let me give you the definition in a second. But the technical definition, it measures the likelihood of an event occurring. Okay, probability of an event is always between 0 and 1. Okay, so you can write a probability, and these would be written in a decimal format if it's between 0 and 1. Or you can write it as a percentage between 0% and 100%. So there's two ways you can write it. Well, three really. You can write decimal, you can write fraction, or you can write it as a percentage. So those are all options, and I'll show you the different ways you can write it today if it doesn't specify. Now, if you have a probability, it says an impossible event. So if something can't happen, like let's say I was rolling a die and I said, what's the probability like a normal dice, and I said, what's the probability I roll a 12? You'd be like, Miss Carter, you're crazy. That has a probability of 0. If an event is certain to happen, so again, let's say I rolled a dice and I said, what's the probability I roll 1, 2, 3, 4, 5, or 6? One of those has to happen. So a probability of something that has to happen is 1. Now, for either one of those, if you do that as a percent, this one would just be 0%, and this one would be 100% if you did a percentage instead. All right, now, just before we move on, I probably should have put this, I'm going to just go to the top of the page real quick. If you see the notation, like a capital P and then a parenthesis, the P is standing for probability of, and then whatever is inside there will be the probability of what you want to happen. So the P just stands for probability. You'll have little parentheses. A lot of the notation looks like this. And whatever you want to happen, they'll put inside the parentheses. So that's what that notation is going to mean. So you'll see that kind of as we go down the page a little bit. Okay, now, two kind of terminology points for theoretical probability. Some of the Math Excel questions call this the uniform probability model, but it's the same thing. So theoretical probability is what should happen. Like theoretically, what should happen, or what's the probability based on what you think should happen. Now the actual calculation of this is the number of outcomes in the event that you want happening over the total number of outcomes in your sample space. And sample space is literally just all the possible things that could happen. So we're just going to do a couple examples for theoretical probability. So we're not doing an experiment or anything like that. This is just, in theory, what should happen. Okay, so sample space is all the possibilities that can go on. So I just have, my first example just says, we're going to flip a coin. So if you just had like a normal, like a nickel, dime, whatever, what are the possible things that can happen when you flip a coin? If I flip a coin, what could possibly be the result? Heads or tails? I was getting nervous, like everyone was being very quiet. Okay, so heads or tails, that's your sample space. Okay, now theoretically speaking, if I flip a coin and it's a fair coin, nothing weird or anything like that, this is just saying, what's the probability that I would flip heads? Does anybody know? 50%. So I'm going to write this as a fraction here real quick. So one of the outcomes is heads out of 2 total outcomes. So it'd be 1/2. You can write that as 0.5, or you can write that as 50%. Any one of those three, unless it specifies in the question how they want you to write your answer, is correct. 1/2 is between 0 and 1, 0.5 is between 0 and 1 as your decimal version, and then 50% as a percentage. What would you tell me for the probability you'd flip tails? Same, yeah, right. Okay, you don't have to write these all out again, but 1/2, 0.5, or 50%. Any of those are okay. All right, now, let's say I had a normal, I'm just going to have one die if I roll dice, if you want to think about that. So normal six-sided die. What are all the possible things that could happen if I rolled a normal, just one dice? Die, I shouldn't say dice. One die. Yes, ma'am. Okay, so we could do a 1, a 2, 3, 4. Like those are all the possibilities. Okay. What? And you can do fraction. Let's just do fractions for these. What is the probability you would roll a 1? Why is everybody so quiet? 1 out of 6, right? And if you can reduce the fraction, do that, but in that case you can't. If you want to write that as a decimal or a percentage, it's kind of got a weird repeating decimal, so I'm just going to write it as a fraction. Okay, how would I figure out the probability? This says that I do not, this is saying not 6, so what's the probability I don't roll a 6? So think about all the options that would not be 6. How many of those would I have? Perfect. 5. All the other numbers, so 5 out of 6, 1, 2, 3, 4, 5, those would all be options. So it's 5 out of 6. What's the probability in that group that I would roll an odd number? What do you think? Say that one more time. 3, 6, or 1/2. That's exactly right. Perfect. Okay, 3 of those numbers are odd, 1, 3, 5, and out of the 6 total. Is anybody having a question? Okay. Now, this is all, we're still doing theoretical here. All right, so I have this weird spinner, and it doesn't say this, but it should. So all those are evenly spaced little sectors that you see the numbers on. So if we spun a little arrow around this and said, okay, what is the sample space? I would list out each of the little pieces. So if you look here, you have, and I kind of darkened mine in because my copy was really light, but a couple of the numbers didn't show up great. But I have 3 ones. So when you are listing the sample space, you would have to list each of those individually. So I have 3 different ones. And I have 2 2s. I have 2 3s. And I have a 5. So there's 8 total spaces, so I have 8 total outcomes. Okay, so in my sample space, right, we have 8 different things. They're not, some of them are repeated, but there's 8 spaces on the little spinner. What is the probability that you would land on a 1? Let's just do a fraction. What's the probability I would land on 1? 3, right? 1, 2, 3, and there's 8 total, so 3 8s. Done. Now, what's the probability I'd get a 2 or a 3? If I spun a little arrow around that. 2 or 3. What do we think? 1/2. If you notice this, you have 2 2s, 2 3s, so 4 total out of 8, and then that reduces to 1/2. What's the probability you would land on a 6 if you spun this spinner? What do you think? 0. Doesn't exist. There's no 6 on the spinner, so we can't do that. Now, I don't know if you guys are going to know this or not. Do you guys know what a prime number means? Okay, so it's only factors or 1 in itself. I see a lot of people shaking their heads. So let me just, only factors are 1 in itself. 1 is a prime number. 2 is the only even prime number, but 2's factors are only 1 in itself. 3 is a prime number. 5 is a prime number. 7 is a prime number. 9 is not, because 3 times 3 is 9. So the next one would be 11, and on. So it's just, prime number just means that its only factors are 1 in itself. What's the probability on this spinner, if I spin it, that I would land on a prime number? 8 out of 8. This is, you have to, this is certain to happen because all of those on the spinner are prime numbers. You can just do 1, or if you want to, 100% this will happen. Does anybody have any questions? So theoretical probability is just what you think should happen in theory. You're not actually performing any experiments or anything like that. So then the difference here, we're going to talk about experimental probability next. This is to involve some kind of experiment or some kind of data collection. So I'm going to just write down here. This is based on an experiment. So like if you sit there and, you know, flip a coin 100 times or something like that, that would be an experiment. Or this can also be based on given data. So if they give you some information, that's considered experimental probability as well. Some kind of trial has happened or some kind of data has been collected. Okay, so this is different than theoretical probability because we might think we know what's going to happen, but based on the experiment, what's going on here. So this is calculated by the number of outcomes in the event that you want divided by the number of trials in your experiment. Or like sometimes this will be a data collection thing. It'd be like the number of people in your data collection or something like that. So in this question right underneath here, just to kind of illustrate the difference here, this says you flip a coin 10 times, right? Okay, now theoretical probability, we already did this. We said half the time we should get heads and half the time we should get tails, right? That's what should happen. This one says when we did this, we got heads 7 times and tails 3 times. So based on this experiment, if I flip the coin 10 times, the probability for my experiment that I got heads, this would be 7 out of 10. And it says we got tails 3 times, that would be 3 out of 10. So there's a difference between experimental and theoretical because it's got to be based on what actually happened in the trials that you did. So it might not match up with the theoretical probability. All right, so I've got another little example, and this one actually has like the data collection piece. So I've got data collected here, and it just says the teacher conducted a survey and asked basically all the students what color eyes they had in his classes, and then it shows the results. So, bless you. So we have 12 people with blue eyes, 58 with brown, 2 with green, and 8 with hazel. All right, so does anybody know like how could I figure out how many trials are here? Like how many, like when I set up my probability, it's going to be something, the number of people in my event over the total number of trials here. What would you do to figure out the total number of what's going on here? Exactly. You're just going to add up all the number of students. Basically, like each student would be considered a trial. If you add these guys all together, you're going to have 80 total students in this example. So that's the number of trials in this scenario. Okay, so experimental probability is based on what's in this guy's class. So what is the probability if I randomly pick somebody out of one of his classes that they would have blue eyes? Like how would you set that up? Austin, what do you think? Perfect. Okay, 12 out of 80. Now, as many of you know that had me last semester, I'm just going to reduce this on here. So I'm going to do 12 divided by 80, and then I'm going to hit enter, so it gives me a decimal. If you want to write this as a decimal, that is completely fine with me, so that would be 0.15. And if you want to convert it to a fraction in lowest terms, if you don't feel like reducing, which I never do, just do math, enter, enter, and it'll convert that to a fraction in lowest terms for you. So this would be 3 over 20. So if you're working on like a test or quiz or the Math Excel, it's going to want you to reduce the fraction if you can. So 3 out of 20, 0.15. If you actually like the percentage better, does anybody know what that would be as a percent? The 15%, you're just going to scooch the decimal over 2 spots. So it'd be 15% chance I'd randomly select somebody out of his classes. They'd have blue eyes. Okay, how would you figure out probability if somebody would have brown eyes out of his classes if we randomly picked one of them? It's so quiet today. If I look at the table, how many people have brown eyes? 58. So all you got to do, just do 58 out of 80 and you're good. And I'm going to go ahead and do 58 out of 80, figure out the decimal real quick. So this is 0.725 if you want to write it as a decimal. I'm going to do my math, enter, enter to delete or to reduce that fraction. So it's 29 over 40 if you want to do a fraction. If you want to do a percent, I would just scooch the decimal over 2 spots. So it'd be 72.5%. So like a ton of people in the class have brown eyes, obviously. And that's pretty typical just for the entire population. Okay, So probability I have green, right, would just be there's 2 people with green eyes out of the 80 total. So I'm pretty sure I can reduce that fraction decently without my calculator. So that'd be 1 over 40. Let me see what that is as a decimal. This is 0.025. So if you want to convert that to a percentage, we would scooch the decimal place over 2 spots. This would be 2.5%. I'm just trying to give you guys all the options here in case any of the questions specify, like if they want a fraction, if they want a decimal, if they want a percent, so you'll know how to do that. And then I got one more with the hazel eyes. So if you look at your chart, you got 8 out of the 80 people. And so that would reduce to 1/10, which would be 0.1 or 10%. You do not need to write all these options for these answers. I'm just trying to cover all the bases in case the question asks you in a specific way. If it doesn't ask you in a specific way, it's your choice. Now, how would we figure out, like still using this table, how would I figure out the probability I'd grab a person that has blue or green eyes? Like, how would you figure that out? Okay, so what would you do for that one? Yeah. We could just go ahead, add them right together. We could add the percentages, you could add the fractions, you could add the decimals, however you want to do it. Just add them together. That's all you do when you have an or statement. So total, like blue and green here, if you wanted to do like separate problem, like as a fraction there, this would be, let's see, 7 over 40 as a fraction. And if you want to do it as, let me see, what is that as a decimal? This is 0.175 as a decimal, 17.5% as a percentage. So again, you could just add the two together that we already calculated, or you could do it separately. It's totally up to you. How would you figure out the probability that we grab one of these people and they do not have green or hazel eyes? Not green and not hazel. There's a couple different ways you could do this. Yeah. Perfect. That's probably what I would have done. You can just add up the green and hazel, right? So together, this is 10 people. And we want to exclude them. So out of the 80, it'd be 70 out of 80. The other thing you could do is you could, the other two colors that we have, blue and brown, you could add those together, just do 12 and 58, and that would give you 70 out of 80 as well. This reduced to 7/8. Let me see, I don't know. That's a nice decimal. Yes, it is. This is 0.875, or as a percentage, I feel like this is a little extra, but 87.5%. So most of the people either have blue or brown in the class. Okay, does anybody have a question? Experimental probability. Okay, now this little Venn diagram, this is also considered experimental probability because I'm collecting data. It's just a little bit different representation. So we're going to have a little Venn diagram here. I'm going to go through and make sure you guys understand what the numbers in the Venn diagram mean. So it says all the members of a club were asked if they eat apples, and they just used an A for that circle, or bananas, so we use a B for that circle, and the results are displayed in the Venn diagram. Okay. Now, how could I figure out how many total people are in this club? Like, what would you do to figure that out? Like, what would you grab from the Venn diagram? How many people are in the club? Okay, we're going to just add every single one of these numbers. Let me do, before I do this, let me ask you. Okay, like, what does the 17 mean? These people like just apples. Okay, what is the 52? Both. Okay, you guys get this. The 20 would be those people just like bananas. And what about this weird 41 down here? Neither. Good. Okay. Now, each one, and I know there's one that overlaps, but the 52 there's 52 people that fall in both of these categories. So you'd actually just literally add the 17, the 52, the 20, and the 41 all together. So there's 130 people here. Okay, how would you figure out the probability that people would be willing to eat apples and bananas? Like, what would you do to find that probability? If I randomly select somebody from this club. Perfect. There's 52 in the middle here that eat both, so you would just do 52 over 130. And again, I know I don't really specify in here how to write this. So if you want to write a decimal, this would be 2/5 if you reduce the fraction, 0.4 or 40%. I would take any of those answers if it doesn't specify. All right, now, how would you find the probability that the person would eat bananas? You got to add these. Good. Okay, so 52 people will eat both, so you would have them included, and then the 20 people that will only eat bananas, but all these people would eat bananas. So add those two guys together, but keep the bottom, the 130. So this is going to be 72 out of 130 to get your decimal percentage or fraction, depending on how you want to do it. So let me, ooh, this is a nasty decimal. Okay, so 36 out of 65. Let me go, I'm just going to go two decimal places on that. It's about 55% or 0.55 as a decimal. And again, unless it specifies, I would take any of those answers. Does anybody have a question? Okay, now, we did theoretical, experimental, and now we're going to look at geometric probability. So geometric probability is going to involve some kind of area or some kind of space. And the way you calculate this probability, it's going to be the area of the event that you want to happen divided by the total area of whatever the object is that you're working with. For this example, we're going to work with this little dartboard that I have constructed on here. Okay, now the dartboard, it tells you in the directions, it just says it's a dartboard, but I've got some good labels on this. So the bullseye part in the middle has a radius of 3, and then each of these circles that come out from the bullseye, the space in between there is going to be 2 inches, and we're going to talk about area here in a second, but we're going to have our answers. I'm going to have us leave them in terms of pi so they're nice numbers. Now, just in case you forget from geometry, just area of a circle is pi r squared. So, if I wanted to find the area, the entire dartboard is just one giant circle, right? All I would need to find the area of the dartboard would be the radius of the whole thing. Does anybody know what the radius of the whole dartboard would be? Can you tell? What should the radius of the whole thing be? What do you think? Good. All right. All you're doing, like this is 3, then it's like 2, 2, 2. Just adding those up. So 3 plus 2 plus 2 plus 2. This is 9. All right. So all we got to do for my area of the entire dartboard, this will go on the bottom of my probability. This would be pi times 9 squared, and I said leave it in terms of pi just so we don't have to mess around with that. So I'm just going to square the 9. This would be 81 pi. Okay, need that. That's going to go on the bottom of my fraction for any probability because that's the total area of what we're looking at. Okay, now find the probability that I get 20 points. So we're just saying if we randomly throw at this, what's the probability you would land in the center part? Okay, so the 20 point, that's the bullseye area. So I would have to find the area of that piece and then over the total area. How would you find the area of this center shaded in piece? What do we think? Pi times 3 squared, your radius, right? Radius of that little inner circle is 3, bless you. So it's just pi times 3 squared, which is 9 pi. Okay, so that's the radius of the bullseye, or sorry, the area of the bullseye. And then our actual probability here, it's the area of what we want to happen, which would be the 9 pi divided by the total area. And this is why I wanted you guys to leave it in terms of pi, because we can just cancel those right on out. And 9 over 81 would reduce to 1/9. That would be the probability. And again, you can do decimal, fraction, you can do percentage, whatever your preference is. I'm just going to leave it as a fraction there. All right, now this is a little bit trickier. I'm not going to lie to you. Okay, so what is the probability I land, and I'm going to just color this here real quick, in the 5-point section or the 10-point section? Okay, just coloring that a little bit. Fired, I can't color inside the lines. Okay, pretend I did a better job coloring that. Okay, now, we're not including the bullseye in this because it says 5 or 10 points. So how would I find the area of what I shaded there with my lovely yellow highlighter? Any idea? Say that one more time. Okay, he says pi and then 4 squared. If I did that, I feel like that would give me, like if this is 2, it would give me the area about, don't draw this on your paper, like right in here. So I think you're on the right track. I don't want to include the bullseye though. So like 4 squared is not going to quite work. What do you think? Perfect. Okay. If we do, like, just ignore the outside ring for a second. This is going over 4 from that. If we go over that whole thing, take, the radius would go 3, 2, 2. So you would have pi times 7 squared. That would be that entire yellow part, and then the bullseye included. But we don't want the bullseye, so I'm going to subtract that. So that's the pi times the 3 squared. That was your bullseye, right? So we just got to exclude that. That's kind of tricky how that's worded. So this would be 49 pi minus 9 pi. And so, again, that's why I'm having you leave it in terms of pi. It makes it easier to work with. You just do 49 minus 9. So this is 40 pi. That would be the area of just that yellow part that I colored there. And then all we have to do for our probability, the area of what we want is 40 pi over the entire area of the dartboard, the 81 pi. The pi's cancel out, and actually, I don't think that fraction, maybe it does, hold on. I don't think that fraction reduces. No, it does not. So this would be my probability, 40 out of 81. But the pi's do cancel, so it's a little bit easier to work with if you leave it in terms of pi. Is anybody having a question? Okay, talk for a really